Uh, Today, we are happy to have Yuhan Liu telling us about entanglement in the vertex state, conformal interface approach. Over to you.
Hello, everyone, and nice to be back in Chicago and seeing many of you. So as the title suggests that today I'm going to talk about the topics that are related to the quantum entanglement, which is mostly based on these two papers that we have recently. So one of them we have done last year, and the other one that hopefully we are going to post that soon. We are like finalizing that. And first, I want to mention my collaborators, my PI Kinsey, and postdoc Yuya, Fermion, and Jonah. Everyone knows Jonah here, yes. Okay, so let me start. So we are going to focus on the quantum entanglement, and the specific question is that what the quantum entanglement can teach us about the different phases of matter. So say that suppose we look at the topological system, and we know that in that case we will have a universal constant that is related to the total quantum dimension for the system that we study. And suppose we look at this entanglement spectrum, if we see the zero mode in the entanglement spectrum, that typically says that we have something topological happening in the system. And move on to think about the system with the phase transition and at the critical point. Using the methods from the topological theory, we know that in that case, the entanglement will also take the universal form with the coefficient related to the central charge, and using that entanglement scaling formula, we can also know the central charge for the corresponding CFT. And then say that suppose we want to do some geometrics by using the structure like the quantum network. Understanding the quantum entanglement structure for the given space that we want to represent can also help us to choose a proper quantum network representation. That is also an important thing to know. And recently, there's a lot of interest in the so-called entanglement transition. And the two famous examples are the measurement in field space transition. That is basically saying that you have some random circuits, and you assume the measurement rate in that circuit, you can see the transition for the entanglement scaling from the volume law to the area law. And the other kinds of the entanglement transition is related to the many body localization, to the thermalization transition. So that is quite interesting. And quantum entanglements also play an important role when we study the holography, like the ADS correspondence, and we want to compute the entanglement on the boundary and the problem. Okay, so up to this point, that we are basically only talking about the so-called bipartite entanglement. Means that we have a total system, and we break that into two parts, and then we compute this Neumann entropy that related to one piece. But then, however, when we think about this quantum manifold system, in principle, that we can partite the system in a more complicated way. So in the more general cases, that we can also think about the so-called tripartite entanglement, which is going to be the focus for the talk today. Like what happens, suppose we want to compute the tripartite entanglement for the basis of matter, and what can that going to teach us? Okay, but then, however, little is actually known about the so-called tripartite entanglements. So as a comparison, when we talk about the bipartite entanglements, we usually will use this definition for the von Neumann entanglement entropy, and the area log piece in the von Neumann entanglement entropy as like roughly counting the number of the bell pairs that is crossing this entanglement boundary. Like here that we have that green line to be the so-called boundary. And as I mentioned before, when we do the computation on the topologically ordered system, we are going to get the topological piece. So basically, we can also ask the similar questions when we consider the tripartite entanglements. So say for the simple case that we only have 3 qubits from a famous paper about 20 years ago, and we know that in that case, the 3 qubits can only be entangled in 2 different ways, meaning that we can either have the so-called GHZ state or the W state. However, for the quantum manipulated system, we have so many qubits. So one can imagine that in a general case, we can have a really rich types of the tripartite entanglement structures. And related question is that how to define the proper entanglement measures to detect the different types of the entanglement structure. And specific question is that suppose we compute that on the topological system, what kind of the signature that we can see? So many are still the open questions that are very interesting. Okay, so during the past many years, people have proposed different types of the tripartite entanglement methods. Say like the neutral information and the negativity that probably people are quite familiar with. But today, I'm going to focus on a quantity that is actually proposed quite recently back in 2019, and it is called the reflective entropy. So let me first talk a little bit about the definition. So basically, the reflective entropy is related to the purification of a reduced density matrix. So say that suppose we start from a reduced density matrix supported on A and B, and we can say do the atom decomposition. So that is the first situation here. And then after that, we basically first we take the square for the lambda, and then after that we split the graph into the cat in the second copy of the Hilbert space. So
Is that description basis independent?
So actually, because we haven't specified, say, what is the basis on the second Hilbert space. So that is roughly saying that on the second Hilbert space, you can choose any basis you want, because we haven't specified that. But result for the result for the reflective entropy will be independent for the type of the basis.
It's like the Schmidt rank where you sort of minimize over how many of the die. Once you do that. What am I doing? I'm minimizing something? Like when you do the purification, essentially because the purification is unique, it's different.
Yeah, so actually, so maybe I can write down. Yeah, imagine that when you have a matrix of area that say one kind of say make value so you want to kind of say such that so say for this effort we are going to get the original matrix. So that is the so it's difficult that that you can do this purification in many different ways. And the twice here is so the twice here is the so-called canonical classification in a sense that a star has the same size as A and a B star has the same size as B. Yeah.
So are A star and B star basically just the dual spaces of A
Yeah.
and B? But then wouldn't the purification depend on like some choice of canonical isomorphism between the vector space and the
But
spool?
doesn't.
Yeah,
the
yeah.
inner product-
Hmm?
Doesn't the inner product already give the correspondence to the dual?
Like
In that case?
Ah, right.
Yeah.
So there's a fixed canonical isomorphism. I see, that's yes.
right. So now we have a pure space in this larger pure space that has the double the size of the original pure space. So now we have a space, so we can do whatever we want. So here the definition is that we take that space and we trace out the path from B and B star, and with that we have a new reduced density matrix supported on A and A star, and then finally we use that to compute the usual from Neumann entanglement entropy. So that is the basic definition for the reflective entropy. So I think that's the definition, and one may ask that why is it an interesting quantity, and why even people want to care about that. So say we have different versions for the answers depending on which community that you are talking about. So say suppose you talk with the high energy theory community that that probably they are going to give you this answer that it is interesting because the reflective entropy has a really nice holographic work. So because we have a lot of high energy people here, so maybe I can talk a little bit about that. So the basic idea is that say in this case that suppose we want to compute the entanglement entropy on the boundary, we know that we will need to compute the minimal surface. So in the case that when A and B are really close to each other, then you are going to see these two are going to be your minimal surface. So then people call this region to be the local entanglement wedge. And then the idea is that people want to define something for the entanglement wedge cross section, which is basically saying that they want to find the minimal line inside this entanglement wedge. So in this simple case, because it is matching, so we know that this blue line here is going to be the minimal line. So that is the so-called entanglement wedge cross section. So for long time, people want to find that what is the holographic rule for this entanglement wedge cross section, and that is actually the motivation for proposing this quantity called reflective entropy. So the basic idea is that from here, because we cannot double the silver space, so now that, so we are actually kind of focused on this region, and then because we want to, find the, Neumann entanglement entropy, so that is why we want to find the minimum surface in this region. So that actually turns out that this line will be your minimal surface, and the proposal is that the refractive entropy is twice the entanglement wedge cross section. So it is the holographic dual for the entanglement wedge cross section. And that is why people in the high energy community is quite interested in this one. But because I actually identify myself to be a condensed matter person, so today I'm going to more talk about this quantity from a more condensed matter point of view. So from the condensed matter perspective, it is interesting because it actually captures the non-trivial tripartite entanglements. So people define this quantity for the Markov gap with a difference between the refractive entropy and the mutual information. And suppose we first take some simple space to compute that what is the value for the Markov gap, we can already see some really interesting results. So for the delta, because we only have the 2 qubits, so the density matrix is a pure state, and in that case, the Markov gap is 0. And as I mentioned before, when we have 3 qubits, the 3 qubits can entangle in 2 different ways. And suppose we take one of them, which is the this state, and we compute the Markov gap, we find that it is also 0. And for a more general case, if we consider the ground state for the one-dimensional gapping Hamiltonian, one can also prove by using some methods from the matrix product state that in that case the Markov gap will also be 0. And the other case that is being 0 is the triangle state. So and because we can see that spatial, and one can also prove that for this kind of state, the quality is also trivial. And also for the stabilizer state, like the clipper circuits, one can also prove that this quantity will be 0. But then, however, suppose you look at the ground state for the one-dimensional critical system, you will actually get a positive quantity. Yeah.
So can you give some intuition for what exactly tripartite entanglement is supposed to capture, like what kind of coordinations? Like I understand that it's 0 in all of these states, but for example, I don't have any intuition of why you expect it to be 0 in these states.
What's a state where you want it to be non-zero?
Right. So suppose you look at the W state, then in that case,
Maybe
the quantity will be positive. Yeah. Okay. Yeah, so that is saying that this quantity can tell the difference between the W type of the tripartite entanglement and the J type of the tripartite entanglement. So that is kind of nice because we can tell the difference between this two types of the tripartite entanglement.
So this is the total central charge in H plus your zero.
So because actually here that so in this case that we are talking about this one dimensional case. So I think in most cases that we talk about for the one-dimensional system, we have take left equals to the right. But then suppose we talk about say the boundary for the two-dimensional case, then that will be a little bit tricky. Yeah, and in that case that that sometimes we need to distinguish the total charge and the total charge. But for the 1D case, we always talk about the whole case. Right.
There is a sense in which the tripartite entanglement is associated with three regions that become.
Yes, which is the case that I'm going to talk about later when I talk about the two-dimensional system, that you are going to see that junction. Right, and also because there are many high energy people here, so I also want to mention this result that say suppose we take a holographic space and we compute this quantity, we are going to see that it is actually proportional to 1/G. And in the many cases that we are interested in this N goes to 0 limit, which is saying that it is actually a very big quantity. So that is saying that the holographic space actually have the non-trivial tripartite entanglement. So I think for a while that people kind of think that the holographic space only have the bipartite entanglements, but now that because people have this result, so that is kind of saying that it is actually not true.
So this is assuming this description that you have in the physics.
Right.
So what's the status of the proposal? Like it will damage
You mean this direction? So I wouldn't say that yeah, so I would say that like currently probably it is just a conjecture. Yeah. But people have confidence to believe that it's probably true. Okay, so now we come back to the next method point of view. So the next question that we want to think about is that suppose we think about a two-dimensional system, then what can we see? And what can we learn from computing this quantity? And that is going to be.
And it seems like this tripartite entanglement is somehow like topological in the sense that like if you have a 1D gap ground state, it's 0 no matter what kind of local perturbation you put into it. That like it's consecutive to local perturbation. Like if you have bipartite, if you have like local perturbations near the cut, then that would change your bipartite.
I actually haven't think about that from this perspective, and we should talk later. Yeah, that sounds a nice interpretation for this quantity.
One is also weird because you can't really draw a junction. Right?
Yeah, I guess maybe it's more relevant to 2D.
So, let's now, move on to talk about this 2D case. So basically, we want to compute, the tripartite entanglement in the setting that we have a topologically ordered ground state in these two tripartite dimensions. And with the tripartition that Clay, mentioned before, that we, actually have this region A and B and C join at one point. So you can see that there is a junction. And so let me first talk about the results. So the key result is that in this case, the Markov gap will also be related to the intercharge for this system. So because we have this bulk and boundary correspondence in the topological order system, so on the boundary we have some 1 + 1 dimensional depth, and you can think that it is the central charge for that 1 dimensional depth on the boundary, and this result is rigorous under this following two assumptions that we consider the system which is deep inside the topological phase, and we are talking about the chiral phase. Yeah, so kind of advertise that it is an important result because the Markov gap can capture significant information of the topologically ordered ground state that is beyond the topological entanglement entropy. And one of the interesting points about this result is that it is actually insensitive to the single corner contribution. So say suppose we go back to the last case that
So
in the
in this case, C is like C left, right? It's chiral central charge.
So rigorously speaking, it is the so-called ungappable part
C
of
left
the
minus C, right?
total charge.
C left minus C, right?
So it is the ungappable part of the left plus the right.
Is that just C left minus C right? What is it as a function of C left minus C right? You're talking about, you have a 3D topological field area of one boundary, right?
Mhm.
So I would have thought you were talking about the chiral C left, at least the rack, a holomorphic part of it. Is that what you're doing?
What type of topological order phase you have? We need to do, so simple any if to the. Can we have a non-chiral step?
Yes.
Chiral center is zero, is zero happening?
So typically say when you talk about the simple case, we'll have the topological interval. In that case, because you can get the boundary, so in that case, this ungettable total central charge is going to be 0 because it is gettable. But that, however, that you can
What is the
think
definition
about.
of the ungappable central charge? It doesn't know. I have a CFT, what is the ungappable central charge?
Right. So if I remember correctly, then Michael has a famous paper that kind of talks about the case that even that, say you have some non-chiral theory, sometimes you cannot happen.
I know, but it's a funny way to say it, because the C, I think by definition, C is just a function of C left and C right. But I know that there are systems with C left equals C right that can still not be gapped. But we can't tell that just by looking at C. We have to tell that by looking at something else.
Yeah, some more information.
You're talking about the higher central charges? Is that what you're talking about?
No, what is your definition for the so-called parasitic charge? Like the different.
Well, there's some kind of complete list of partition functions that have to trivialize in order for the theory to be gappable. Is that what you're doing, the opinion?
definition
No,
is
it's
true.
true.
That's like, but the definition, oh, I see, it's a minimum, it's not sufficient, the particle number.
Anyway, I just want to know what C, what is the, I hand you a CFT, what is C?
Yeah,
What is C in that formula?
so say that, suppose that it is a chiral theory, then it is a chiral cycle path. Say that, suppose you take this integral particle form system in a bulk, then in that case, you will have C equal to 1. And then suppose you have the correspondence in the bulk, because in that case, you can get the boundary, so you get this, this quantity will be 0. Suppose that you take a system that is non-chiral, but you cannot get the boundary, then in that case, when you compute the quantity, it will still be positive.
How do you compute? What is the formula?
So, yeah, so, can I say that this is the formula? Yeah,
Okay, maybe we can talk about that.
yeah, sure, yeah. Right. Mhm.
I mean, this is some calculation in the two DCFT, so the answer is some data about two DCFT. Well, maybe it's a calculation of the 2 plus 1 ball, but it's under some rational theory, so.
Yeah.
But what we know for sure is that if you can't cap the C,
Mhm.
the C will be constant.
Yes. That's right.
On the proof of fermion, that mechanically cap on that, but
Well, I know how to check if there's an obstruction, the gap in the boundary that along the line you're saying, but what I don't know is how to formulate that as a single number. Right, like, in fact, I didn't think anybody knew how to formulate it as a single number.
Right.
So that's the part that I'm finding confusing. I understand that there's a sequence of obstructions that prevent gapping the boundary, but I don't understand how to formulate that as a single number. Right.
Yeah, so, maybe we can talk about that later.
Okay.
See that, right, so, we have talked about the second case in this conjecture, and the other point is that, suppose we remove this seed inside the topological space condition, and in that case, this quantity will actually be the lower bound for the amount of gap. Okay, so we kind of know the result, and in the following that I'm going to try to talk a little bit about these technical details. Hope that won't make you feel too boring. So the basic idea for this calculation is to use the famous boundary correspondence that we mentioned before, that we have a topological order in a bulk. In that case, we have a CFT on the boundary, and specifically, suppose we want to compare the entanglement. The phrasing is that the calculation for the entanglement in the bulk can be related to the so-called left-right entanglement entropy in this 1 plus 1 dimensional boundary. So we probably don't really want to care about the these technical details, but the basic idea is that we want to use a boundary condition to define a boundary space. And roughly speaking, the boundary condition tells us how to match this chiral and the anti-chiral copy. And then we
This is
have,
the boundary, where is the boundary in one plus one equals the plus?
oh,
Picture,
uh,
figure out the picture of 1 plus 1.
right, so it is like that. So here we have this cylinder to be 2 plus 1 be out.
So
And
it's
then-
a filled-in cylinder, but where's the boundary of the 1 plus 1 boundary of the 1 plus 1?
Right, so here you can see this circle, so that is why we want to cut the cylinder into 2 pieces, and then we want to compute the entanglement entropy related to the piece A.
But if there's really a boundary in the 1 plus 1, why did you stop at the Ishibashi state?
Oh, sorry,
Ishibashi states are not boundary states.
so I think what I was saying is that what I was saying is that we have a boundary for this 2 plus 1 system, and the boundary is a circle, and we cannot find this boundary state on this circle. That's
So that
valid.
means the 2 bounds where there could be a linear combination.
Right. So say that because all the Ishibashi states are the solution for this boundary condition. So in the more general case, that say here from this formula, that would take this linear combination for this Ishibashi state. So that is the general solution for this boundary condition.
In general, an Ishibashi state is not a boundary.
Mhm.
The general boundary condition is a non-trivial linear combination. of
Right.
Ishibashi states.
That's right.
With
So
the
I
drive
think you were talking about the so-called Hardy state that say that say suppose you have a physical boundary. I think and then in that case you can identify that boundary state is a Hardy state.
So you don't have a boundary here, and in that case, why? Aren't you cutting the space into 2 pieces? Isn't there a boundary condition at that cut?
So here it is say not the physical boundary, but more like this entanglement boundary. So in general, we actually don't have to require that it is a Hardy state, that we can do something more general. Because for the Hardy state, that you need to take some specific points for this linear combination. Here we can do we can choose something more general.
Why? I mean, if you don't choose the Cardi states, it's like saying the degrees of freedom at the cut are related non-locally. The Cardi condition is the condition of locality.
Mhm. So I think my way to say to understand this problem is that say suppose when we compute the entanglement entropy in a 2 plus 1 D block, say suppose we want to compute that on the torus, so in that case we can have many different generate ground state, and then we can think about say to be the general linear combination for the generate ground state. So my understanding is that by the analogy that when we think about this left right entanglement entropy on the boundary side, we can also take a corresponding general linear combination. So the C here for the boundary state is really related to the C for the 2 plus 1 D ground state.
I don't really understand it.
Okay, yeah, we can talk about that later probably. So, right, so, suppose we, take this boundary space and then we trace out the right moving part, and then we can compute the entanglement, which is defined to be the so-called left-right entanglement entropy. And then with that, we can actually reproduce the famous result for the 2+1 topological entanglement entropy. So what I basically mean is that this equation has the same form as this equation that you compute in the bulk from CQFT. But then, however, that here we want to consider the tripartite entanglement. So, so in principle, we can also compute that from the bulk CQFT, but that is too complicated, so we don't do that. So, so we take the approach to compute that from the boundary safety point of view. And the basic insight is that we want to find a state that mimics the 2+1 ground state near this entanglement boundary. And for the bipartite case, it is the boundary state. So we want to generalize that boundary condition to the tripartite case to define this so-called vertex states. And here the boundary condition is basically saying that now we have 3 copies of this chiral theory, and we want to pair them up. So the boundary condition tells us how to pair these 3 copies of the chiral series, and that is the formula for the most general case. And for the simpler case, for the free fermion, we can write a boundary condition in terms of the free fermion degrees of freedom. So the free fermion case is kind of simple because we can actually find a solution for this vertex space by using some technique from the string field theory. So we find a solution and we can prove that it satisfies the boundary condition. And numerically, we take that solution to compute this Markov gap, and we find the nice results that it is related to this universal quantity. So so that is basically the content in our first paper, and that is kind of encouraging. But however, it is only the result for the free fermion. So we cannot want to say something more general, that if we take the general CQFT, can we have a similar result, or we have something, or we actually have some extra contribution to that? And we want to answer that question in our second paper, and that is related to the title for this talk, that we want to use a conformal interface approach. So the point is that in the general case, even that we have this vertex, say in this 1+1 dimension, it is still kind of hard to find a solution for the general rational CFT. So we want to take a different approach to compute all the entanglement quantities without really needs to solve for this vertex space. And this can actually be done by using the so-called conformal interface approach. So the idea is that we can write the boundary state to be a path integral. So what happens is that we so as I mentioned before, the boundary state kind of pairs up the chiral and the chiral part, and with some regularization factor, which is saying, I suppose we write that in the path integral language, we have this picture. So basically, on the bottom we have this space, and then here this vertical axis represents some imaginary time evolution. And then finally, we have this regularized boundary state at the top. So that is the path integral representation for the boundary states. And suppose we want to use that picture to compute the entanglement entropy. What we are going to do is that we use this practical trick to first compute the Rayleigh entanglement entropy and then take the limits and go to one eventually. So the idea is that in the previous slide that we have the boundary state that kind of like a folder, something like this. So the idea is that we can unfold this boundary state. So suppose we unfold that, we will only have the chiral copies on the theory. And then we follow the rules of the replica trick to glue them together, which means that eventually we will need to evaluate a partition function on the torus with the possible conformal interface in the middle. So that is a little bit technical, but believe me, we can do this calculation and eventually we get the same result. So for the case for the bipartition, it is basically the same as the boundary state calculation, but we just phrase that in a different way. So that doesn't do a lot of things. But the interesting point is that we can use this real point to compute a more complicated case, like the entanglement related to this bipartition case. So say for the vertex, so as I mentioned before, for the bipartite case, we can have this case for the density matrix to be a partition function on the torus. And for the general case for the vertex space, suppose it is a three vertex space, the trace will be a half integral on this two genus. And in theory, it is still kind of hard to evaluate a partition function on the two genus. So on the next slide, that we take an approximation to basically use two copies of this open boundary partition function to approximate the closed boundary partition function. That's a little bit too detailed, but I just want to show that we can do that. And finally, after the calculation and we are going to come to this result. So one of the nice thing for the result for this calculation is that you can see it has a very clear physical interpretation for every pieces that we have an area law term and we have a turn rate to this corner contribution, and we also have a topological piece. So until this point, we only talk about the abelian case. So that is why you don't see the quantum dimension for the anions in this formula. So one of the interesting points in this result is that if we compare the reflected entropy and the mutual information, the corner piece cancels out. So the basically the corner piece is like say when we break the total system into three parts, that if you remember, we have a junction in the middle, but the three pieces can actually have different angles. So here the corner term is related to the angle for the three pieces. Then in general, you can choose the different angle for the different region. So that is saying that no matter how you choose, this piece will cancel. So
sorry, what is the relationship between the genus 2 partition function and these quantities that are on the slide right now?
Right. So that is saying that right. So suppose you want to compute this trace row, it is going to be this genus function.
At some specific value of moduli? A genus 2 surface has parameters, it's like a torus has parameters.
Right. So it is going to be related to this beta and the length for this annulus. But
Are those quantities that are fixed given rho? are those quantities that are picked in a given row, or are they parameters of the calculation? Is the answer that we're trying to compute a function of those parameters?
Right, so eventually that you are going to say, so if you look at this area long term, you will see this parameter related to beta and L. So in that sense, the result is a function for this parameter.
But this would only be the answer in some kind of small or large parameter limit.
Right.
Otherwise, the genus two partition function is so horribly complicated.
Right, so that is what I kind of did. So eventually, that we want to take this beta goes to 0 limit.
Why do we want to do that?
Because here the physical meaning for this beta, say here in this equation, it is related to this regularization, which is not something really typical.
This goes back to the question about what the allowed boundary states are. First, what's special about boldface B? What's so special about boldface B?
Right. So say here's the general linear combination of the different multipartite states and carries this regularization factor. But then in our calculation, that we always take the case that this C being a delta, which is saying that in many calculations that we only take one of these multipartite states.
They're saying it's not, you're only interested in because of that, you're only interested in the genus two partition function in some kind of degenerate limit of the genus two surface. Beta goes to 0, so the genus two surface is generating in some way. That's why you can get such simple answers.
Yes, that's right.
And the answer does not depend on the other one. It does depend on the other one. What are the other moduli? Are they related to this calculation?
Yeah, so you were saying that say for this genus, so we also have to modulate parameters, but I only have one of them.
I seem to remember the formula like 3G minus 3 for the parameters of the higher genus surface, right? So maybe there's 3 moduli, and maybe you told me about one of them.
I see. Yeah. So when I do this calculation, because I take this beta goes to 0 limit, so I actually didn't really think about the other moduli.
But there is an L also, yeah?
So they are kind of being together that in
Beta and L are independent quantities.
beta
And what we call it capital L,
and
those are independent. So I guess L is another one.
but then say beta is kind of like the width and the L is kind of like the circumference. So they kind of combine to give one parameter.
I guess I'm pressing on this because, in the high energy theory literature, there are people who have evaluated the asymptotics of a general genus two surface for any CFT, not just a Chiral CFT.
I see.
So, there's some expression for what that is in terms of the central charge and the sum over operators,
I see.
certain asymptotics of the operators, right? But we don't seem to be matching on with that.
Right, so I actually didn't realize that before, so maybe I will ask you for the reference later. Yeah,
It's not so hard to understand if you think of the genus two surface as, just cut the genus two surface and have operators run in the channels. Then the degeneration limit, you're looking at kind of the asymptotics of the operators running in the channel. So you can write a universal formula out.
so, basically, you were saying that in that maybe, say, one of the channels will dominate, and then we are going to get some results.
Or at least something that you can understand in terms of the spectrum of operators and OP coefficients. That kind of thing.
I see. Yeah. We haven't think about matching that result, so maybe we should. Right, so basically, that is the last slide, and then, yeah, so it's 1:30, so, we don't run, too long. So basically, the summary for this talk is that tripartite entanglements can give us the new information beyond the tripartite case. And then in our papers, we study this quantity using the boundary correspondence and introduce the vertex space. And then because in general case, we cannot stop the vertex space, so we can show the quantities by using the conformal interface of choice. And one of the interesting points about the result is that the Markov gap actually doesn't receive the quantity. Yeah, so thank you for your attention to this point.
In the slide, right, for this one, you had a formula in terms of the S matrix, right? Maybe it's the one.
Right.
Right, but you can just write that out in terms, oh, no, this was for the two dimensional. This is bipartite.
Right.
Yeah, but is there a similar formula for tripartite, like let's say if I have something like U1 level 2 times U1 minus 4, but the central charge is 0, but like clearly it does not admit a gap out here. What would be the C that appears in the formula for those?
Right. So I think in that case that probably you are going to say if you compute the reflective entropy, in that case you are probably going to have some non-trivial topological term. But from the calculation, it kind of seems that for the mutual information that you are going to get a similar piece. But I have to say that currently we are only confident about the results for the abelian case. So
This is a big. The example I just gave something. I guess you want a single abelian factor, is that right? Instead of like, is it allowed to have multiples of abelian things?
yeah, I think
But then
it is okay.
But the example he gave
is a big.
yeah, the example he gave is
Right. So I think in that case that we are going to have this topological term relative to the
Yeah,
dimension.
I'm just interested in the Markov gap once I subtract everything.
Right. So what happens is that you have this piece in the reflective entropy, but you also have the same piece from the mutual information. So when you make the difference, they kind of cancel out. So
Yeah, no, I absolutely agree with that. I'm just wondering what would be the number.
And
If
that
I-
what is H?
Yeah. Because that's like the simplest example I know where the chiral central charge vanishes, but like it still does not admit a gap function and is abelian.
So suppose you cannot get the boundary, then in that case, that you will need to replace the C either the central charge. So you see that's not be right.
I see. Okay.
Yeah.
Thanks.
I mean, these are all coming from the asymptotics of the genus 2 partition function. You're only ever going to see the total central charge.
No, but when it admits a gap boundary, it certainly becomes no. When it does not admit a gap boundary, it becomes
I'm just talking about like in 2D CFT, if you're taking the asymptotics of the genus 2 partition function, the numbers that will appear there will be the total central charge.
Oh, I see.
How will you see anything other than C left, C right, or C left plus C right, or you're not going to see anything fancier than that.
but you could see it see that no.
Maybe you can see C left minus C right, but the idea that like it could be somehow sensitive to the question of whether there exists a gapping deformation, I don't see how that will come back.
Okay, so
Yeah, that's the action.
we are good.